Here is a more detailed schematic for my proposed Brownian Ratchet, which, if workable, would violate the second law of thermodynamics. I don't entertain much hope for this to work, but cannot presently see why it wouldn't work. Hence the matter is still interesting to me. Interesting until proven guilty of error. I'm going to employ 4 one-way clutches in this design, although I think only 2 clutches are actually required to do all this, but showing 4 makes the presentation easier to follow. When the vane is pushed by Brownian movement in one direction, a clutch engages, which forces the upper gear to rotate, engaging the vertical gear, which in turn causes the lower gear to turn in the opposite direction. The lower gear clutch then engages to the drive shaft that rotates the drive gear beneath the mounting plate. The vertical gear is rigidly attached to the mounting plate so that it can't travel around the mounting plate, but can only rotate in place on its axis. Now, if the Brownian motion causes the vane to move in the other direction, the top and bottom gear clutches disengage from the drive shaft, and the forward drive clutch engages directly to the drive shaft, turning the drive gear in the same direction as before. The drive gear then rotates a larger main gear, which raises a weight, thereby storing energy and cooling the surrounding medium, which was at thermal equilibrium. The larger main gear is to accommodate multiple drives from multiple Brownian drive devices. To prevent the weight from dropping, a 4th stop clutch is rigidly attached to the mounting plate so that the drive shaft can never go in the wrong direction. All the foregoing is mechanically sound and will definitely work at the macroscopic level, just like the Kobalt Double Drive screwdriver. The problem is to make it work using Brownian motion at the molecular level of nanotechnology. Our antagonist is the Brownian motion of the clutch pieces. They wiggle, and this would ostensibly render them ineffective in their one-way purpose. That is, the weight would be as likely to drop as to be raised. In the standard Brownian ratchet, the pawl has a spring on it that results in a minimum Brownian energy necessary to lift the weight by 1 increment of the ratchet wheel. Multiplying the number of ratchet wheels then multiplies the minimum energy necessary to advance the weight up by 1 increment. This is not so with a one-way clutch. There is a minimum energy needed to engage the clutch piece at the new level, but multiplying the number of clutches does not add because there are no springs to depress in the one-way clutch. Therefore, if there is a probability that the stop clutch will engage in spite of Brownian wiggling, then multiplying the number of these stop clutches will increase the probability that one of them will engage, disallowing a weight drop. And increasing the number of vanes increases the probability that the weight will be raised, in that the vane can raise the weight by movement in either vane direction. That is, vanes can be effectively ganged to increase the probability of simultaneous force contributions to the goal of raising the weight. Their effect is additive. And making the larger gear accommodate multiple drive mechanisms causes a leveraging of the available drive force, which is a further adjustable parameter, along with adjusting the mass of the weight to be raised. Another relevant parameter is the Casimir Effect on the clutch assembly, if that assembly is rigidly enclosed in a volume whose dimensions are on the level of the mean free path of the Brownian liquid. That is, if we restrict the mean free path of the Brownian molecules. To conserve energy, the number of collisions with the clutch piece must increase while the temperature remains constant. Therefore, the liquid encased with the clutch piece will be at a higher pressure, and the mean free path of the clutch piece will also be reduced by smoothing out the probability of collisions on either side of the clutch piece, resulting in less wiggle. and therefore an increase in the probability of its engagement to stop the opposed rotation of the shaft. And the clutch piece will work better when encased than when exposed, because the clutch assembly as a whole has a much greater mass and wiggles less than its parts, and so cannot transmit a big wiggle to the less massive clutch piece. Such machines can be constructed at the nano engineering level just for practice. If any are really possible, they will begin running as soon as they are made. Although I regard success as unlikely, ruling out such designs by experiment is the right thing to do, especially if one is in the process of practicing the making of things at the nano level. If such a device were possible, one can envision a box, maybe as big as a refrigerator, behind a house. You plug the house wiring into it for electricity, and run an air duct to it for AC in the summer, since the byproduct of electricity production would be cold. There is a problem about turning it off before it could destroy itself by freezing and breaking up the nano parts. If no Brownian Ratchet device can be constructed in principle, then we can state a fundamental rule of nanotechnology. It is impossible to construct a functioning, unpowered, one-way device at the nanoscale.